Hope you guys had the time to have a chat and relax. So we are back now, and before we start with that, so we are gonna try an experiment. So for people on site as well as the people online, please scan this QR code. And because we want to know more from you, so we are gonna try this experiment to check if there was really caffeine in the coffee. And I'm gonna ask you to answer a few questions. And yes, so for the online audience, since we want to make sure that you also are awake, please turn, yeah, I see some likes. Please turn on your camera. If you could do that, that would be great. You're waiting for me. Waiting for presenter.
Yeah, when we go to the next slide.
Yeah. Okay, so. Oh, hello, Alexander. So we have more. Some new faces. UL Solution. Hello. And critical software, that's new. Okay, so we have some brave people that were not sleeping, so that's fantastic. Hey Tilo. Great. So okay, so we have a few questions for you. Can we see the questions? So we tried this earlier, but we now want to check if you're able to identify your own country. So please, on your map, please select where you are from. Where is this? That's a really big dot, honestly. Yeah. So no one's from Germany. This is surprising. Whatever you like. You can, whatever you like. Okay, so there is someone who lives in the ocean. That is very good. We are terraforming. Hi, she. Okay. Oh no. Okay. Well, some people from like Central Europe, we don't really know. This is where? This is Amsterdam. Okay, obviously someone from Rotterdam. What? This is Rotterdam? Yeah. Okay, great. Sarah's not doing well in geography. Okay, we have Brazil, we have the US. There's someone living again in the sea. Someone from Australia. Seriously? I think someone's being creative or is randomly generating position. But okay. Interesting, very interesting. So what about the next question? Maybe we can try that. How would you describe your experience level within SDV? So how brave do you feel? There are many newbies. Okay, we have many newbies. We have some intermediates. Not really. It's 9:40 p.m. in Sydney. Oh, that's fantastic. Cool, Andreas. Thank you for joining. I hope you have a beer or drinks, because for us it's too early to drink now. So, and you have a point. Okay, so the SDV gurus. Do we have some in the room? Who's the SDV guru here? Oh, Danny. So who else is the SDV guru? Because we have someone, we have some online as well. So please, the SDV guru, connect with the newbies, because we have quite some experience. Okay, interesting. Good, nice distribution. It's not Maxwellian, so. Describe in one word why you are joining today. And the answer beers also count. But later. So we are supposed to like, for fun, because you're curious, to talk and meet up. Networking, of course, it's a good one. Learning. Yeah. Impulse exchange. Ancaios. Okay, someone's just going directly to the point. Cola, Escor. Okay, so I would guess that networking and learning are definitely our strong suit, and that's a really good message. Although I was expecting to see some beer. Yeah. Okay, so do take the chance of networking with one another and learning from one another. That's actually why we're here. Great. Next question. What topic related to SDV are you currently working most on? So we are assuming you're working on a lot of things, but please select only one. Toolchain. Ancaios. Okay, Ancaios is king. We have seen it, obviously. Trustable. Ancaios wins. Ancaios wins. Really brutal. Okay. Symphony. U protocols gaining is gaining ground on Ancaios. Careful, careful. Okay. Escor, ecal. Okay, so fantastic. Well, I think that's actually very interesting for me as an example, because we can see what projects are mostly loved. And Kai, you disagree? Can you vote multiple times?
It correlates with the people who are here in person. Yes, that's true.
No, I don't think so, because there are, yes, most likely, yes. At some point I saw 64 votes, so okay, good. Are there bots? Are there bots here? Okay. Yeah, do we have another question or are we done? We are done. So thanks a lot for playing and participating in this experiment. And thank you, Ancaios, uProtocol, and ecal for being so prominent. And we can now move on. We managed to accumulate 14 minutes of delay. So Florian. And we now move on and talk about, actually, the next session focuses on the narrative that we hinted at earlier, which is you can really build an overall platform spanning from hardware all the way to RTOSes, to real-time operating system, and then middleware as well. So the first component of this puzzle is the hardware, obviously. So floor is yours, Florian, and you want one.
Perfect. Hi, everyone. So my name is Florian, short Flo if you like. I'm from the OpenHW Foundation. We are a part of the Eclipse Foundation, and we are doing RISC-V. Just a short question to the audience here physically present. Who has heard about RISC-V before? Perfect. That helps me to skip the next slide, which is just talking about what is RISC-V and how is the adoption growing of RISC-V. You know about that. RISC-V devices, I come to this later. Oh, perfect. So starting, I wanted to talk a little bit about where RISC-V is used today. But before I'm jumping into this, I wanted to show the slide, and we will come back to the slide in the end. What you can see here is kind of a stack. And I would call the stack what we are also seeing in the software-defined vehicle. You're defining different things. The open hardware is here on the bottom. That's really the core, that's the brain of the CPU. Then we are adding the toolchain support around the RISC-V we are presenting. We are coming with real-time operating systems like, for example, ThreadX, but not limited to ThreadX. And we are going all the way up until we come to the SDV building blocks and definitions. So please keep this in mind. I come back later to this. And I want to start with a little bit experience or case sharing where RISC-V is already used today. The first example that is from Facebook, or Meta as they are now called. They made this kind of recommendation chip. This recommendation chip is if you're scrolling to your Facebook and you see a funny cat video, and then you keep scrolling, you will see a second and a third, and it doesn't stop counting because it sees you like them, obviously. To calculate all these things, which is an AI-related task, Facebook has developed this own chip, or Meta, Inside is a RISC-V, not one RISC-V. There are several RISC-V. You see the small PE things. That's what they call a processing element. Each of the PEs has 2 RISC-V chips, and that is already used in the data center from Meta today. Another example, I tried to come a little bit more to Europe. That is Accelerate AI. Not sure if you have heard about them. It's a cool startup based in Eindhoven. They are also doing an edge AI. So what they are aiming for is visualization. You can read number plates. You can have the cameras in your shops. If you're taking something from the shelf, automatically check out, automatically deduct it from your thing. And they are also using RISC-V inside the chip. The chip inside has several building blocks, this AI on-site. There is RISC-V in the main controller. There's RISC-V in the security system. And this chip is also something you can already order today. And that the cool thing for me personally, made in Europe. Another example, and that is your mobile phone. So I don't have a brand because they are all, to be honest, inside under the hood, a little bit similar. And what you're seeing is that you have one main CPU. That's what you're talking about. I have an ARM, it's X78 or it's an N2 Neoverse, whatever. But what most people don't talk about is all the peripheral you have. For example, your touch controller. Already today, majority of these touch controllers have a RISC-V core inside. The storage memory, already RISC-V today, and it goes on like Wi-Fi, Bluetooth, the modems, all the small things we are not publicly talking about because the end user don't really care about it because you're not writing your own software, but all the things which are kind of closed ecosystem, they already run on RISC-V today. Okay, so the question is, we are for a software-defined vehicle today. How does RISC-V come to the automotive world? And first, I wanted to share something which Infineon has announced, this embedded world. So Infineon is now heavily investing in RISC-V already some time. They are also in some research projects from the European Union. And Infineon has shared this picture. You can check by yourself the source. I put it here. The situation we have with RISC-V in automotive is a little bit a chicken egg problem. So we don't have the controllers yet. And that means we don't have the software ready, but to have software, we would need to have the controllers. So Infineon, I really like this. They are starting to make prototypes available, software prototypes, where you have the whole controller, not only the RISC-V core, and you can start simulating it. You can start porting things like ThreadX, for example. So I think that goes into a good direction. Now, another company I want to share is Bosch. Bosch has also within a European project, the so-called Tristan project. They have made this proof of concept where they are really going for the ADAS area. They are having an existing chip, which was powered by another architecture, and they take out the CPU and they put in a RISC-V CPU. Bosch has, for this proof of concept, chosen the open source industrial grade cores from OpenHW. They have one application CPU, the CVA6 configuration A. And then here in the accelerator, where you have the object detection and everything, they have another configuration of the CVA6 that is already taped out. And I think in 1 or 2 months, they also want to show a little bit more in the RISC-V summit in Paris this year in Europe. So you can see that RISC-V is already adapted or starting adoption in the automotive. And I would like to share a little bit more what OpenHW Foundation is contributing and why we think that is also a good thing to have more open source in this hardware domain. Firstly, why the commercial companies join. To be honest, we are here on a software-defined vehicle on an open source initiative. I'm not going into all of these details. We are all joining because we want to share, because we want to have more eyeballs on it for security. There are a lot of good reasons why we should not reinvent the wheel, faster time to market. So I keep it in the slide deck. The members of OpenHW, there are roughly 100 members, different members, for example, Global Foundries. I come to this a little bit later. There is Barcelona Supercomputer Center, CEA from France, There is Thales, there is Dolphin Plan V from Europe, there's Accelera somewhere here. We didn't put all the logos on it. Open hardware really has a strong standing in Europe, and I think that's also where we are seeing the best adoption of RISC-V. Nevertheless, we also see it in the Americas, but also in the Asian Pacific region. Some of our members have given us feedback. So I mentioned Silicon Labs before. Silicon Labs is using some of our cores. They are not really publicly announcing it. It's somewhere deeply in the Bluetooth or in the Wi-Fi chips, but they are quite happy and they are also shipping high volume with it. Another member is Thales, Thales from France. They have a variety of projects. They are a very strong committer in the OpenHW Foundation. They are focusing currently on one core. We call it CVA6. It's an application-ready core. That means you could run Linux on it. And Thales is using this core in a variety of different configurations, bringing it into real applications and real chips. Roadmaps. Now it looks a little bit more commercial. So the Open Hardware Group, we do have a roadmap. I wanted to show this to give you an overview, what we are contributing or what we are able. If you're talking from a performance point of view, you have the CVE2, that's a really deeply embedded core, something which you have to replace finity state machines or something. And then the CVE4 family, that's like a microcontroller unit. That is something where you're running ThreadX on it, a brake controller or something like this. That would be the performance. And then on the top, we are coming to the CVA6. CVA6 performance, that's an application-ready core, what we call it. And that would be something where you can run an embedded Linux on it. There are actually another core, the CV Volley, that is a fully educational core, which is now also coming into industrial designs. The roadmap, what you can see is that even we have different performance, each performance has different cores inside. So for example, we have a S core, which is especially for security, root of trust, over-the-air updates and something like this that helps you to make your communication safe. You have a core for extendability, and you do also have some core for DSP extensions if you need more performance, if you're going in the area of real time. I don't have enough time to jump into all the details. I just wanted to give you a very rough overview that there is not only one core or two cores in the Open Hardware Group. There is a variety of them. We have currently 11 projects and 7 of them are actively developed. The other are already in a good stage where we have what we call TRL5, where the core is ready to put in a commercial design. The big question is, what are we delivering? So the base, what we are delivering is the core. The core itself is written in System Verilog. That is what most of the chip companies are using to make a chip nowadays. And that's what you get. It's fully open source under an Apache license. That means you can take it, you can make a commercial device from it, you can modify it, you don't need to share, but you're more than welcome to share. The core itself is nothing. If you make a chip, it costs a lot of money. So you want to make sure there are no bugs in your chip and you want to verify it. For this, we are also providing a verification framework. The verification framework is also fully open source. So now you got the cores, which is running your program like ThreadX. You're getting the verification to make sure it is behaving as it should inside your chip. Already a good start. On top of this, we also provide the software. So software is a variety. Here we are having the compilers, GCC, or for AI is more like LLVM. And on top of the compilers, of course, various real-time operating systems or also Linux systems. Red Hat is, for example, a member of the Open Hardware Foundation. Red Hat is using our application-ready cores to do continuous integration for their software. So they are making a new software and then they are validating on our core, which they are simulating on an FPGA in the cloud, on the Amazon cloud. They are validating their software is working. If the software is working on our core, fully open source, but it's not working on another core from a commercial vendor, Red Hat then can easily say, look, it's working on the open hardware, it's fully open source, your core is not working, you're not following the specification of RISC-V. That's the background. So course verification, software framework, important, but you also need to have the documentation so you know what we have been thinking when we created the core, to know how to integrate the core into your SoC. We also pay a lot of attention to this documentation here. And then last but not least, hardware. Hardware is a minor part. What we are doing here is to create FPGA images, like on the Amazon Cloud FPGA, but also on real FPGA boards on your site, in your lab, so you can test your software on a simulated FPGA without the need to give it out, and you have a real behavior on the FPGA. Okay, then how to work with the Open Hardware Group. I'm kind of skipping over this. Basically, we are organized a little bit like a company. We have what we call the Technical Working Group. That is a big group of all the contributors. We are meeting normally once a month, and we are talking about the key initiatives. Under this Technical Working Group, we have a variety of task groups, like the course task group. Here we talk about features and design. Then verification task group, super important, where we talk about how to verify all these new features, and also software task groups and a variety of others. There's also a marketing working group. Unfortunately, I have to say most of the members are more on the geeky side. So we are doing a lot of cool technical stuff. We are doing a lot of cool course. We're not talking so much about it, but I'm hoping to change this now in the coming time. Especially Eclipse has seen what we are doing, and they are now helping us pushing on the marketing side more to bring the word out and to get more developers who then contributing, growing the community and making better things available for everyone. Thales is chairing the technical working group, so I'm not going into the detail here. We also do hardware. Someone was asking for hardware, so I have a board here. It's not really our core competence, so we don't want to make the core. We only want to make the schematics for the CPU. We did this board like 2 or 3 years ago to just prove the cores are working. Global Foundries, for example, they are a great supporter of the Open Hardware Group. They taped it out for free. Other members made the PCB. It's all open source. The chip is open source, the peripheral. Some universities help to bring up the board. So the compiler companies used it to fine-tune the compiler, like GCC, especially for this board. I think that's a great initiative to show we have a board. We do have board from other CPUs, but in reality, what we are really aiming for is only this blueprint, only the schematic of the core, and then providing it to other people who are making a chip, people like Bosch, Infineon, but not limited, also Accelera and all these great people who are doing awesome chips and just need to have this standardized brain based on RISC-V. Okay, I thought I put a little bit more of the software side inside, and I feel I'm running late because the first of you start already looking on the watch, so apologize for this. Software task group chaired by Amber Cosm. Amber Cosm is a company headquartered in UK. They also have offices in Paris and in Nuremberg in Germany, so quite an European company. They do a lot of compiler work, especially for GCC and LLVM. If you need a real expert for also upstreaming all this work, they are the go-to. In Open Hardware, they are chairing our software group. That means they are taking care that all the projects we are doing are followed the rules, that everything is open source, that things are upstreamed, and they are also helping the community by questions. We are upstreaming everything. So for one of our microcontrollers, the one here on the board, we have everything fully upstreamed, the GCC, but also the LLVM. The core itself has some custom instructions inside. That's one of the beautiful things about RISC-V, that you can add custom instructions. We have a few inside, and they are also fully supported by this upstream. So core awareness, we have hardware loop support where you don't need to have the compiler doing a loop in software, but it's really supported by hardware with registers, and also some core-specific introductions like DSP extensions for Cordic functions and similar things. Operating systems, QEMU is one of the supporters. That is also upstreamed, then FreeRTOS, Zephyr, and I forgot ThreadX here. I hope Frederick is not seeing this. Then, oh no, sorry, I have it here. I even have it big. I didn't see it. So Linux support is also for our course available. Like I mentioned, Red Hat is especially pushing here, but also the Ubuntu project is running and a variety of other things. There is also an IDE, especially for the microcontroller, that was done by Ashling together with Emberkossen. Emberkossen provided all the compilers. And by the way, if you want to try one of our cores, first, they are all open source. You can download from the GitHub. If you need a compiler, Emberkossen made the effort to put all these compilers pre-compiled on their homepage for free to download. Saves a lot of time. Okay, why to work with us? Because RISC-V is the future. RISC-V is unstoppable, so to say. It will come to the automotive world. It is already arriving here. Now everyone needs to have a RISC-V in the future. You can develop your own RISC-V, but it's a little bit like reinventing the wheel. So come to us, collaborate on the baseline of the RISC-V, and then make your custom extension, which you keep for yourself, for your company, or you're just using the course in different ways. You have more flexibility because you have no license agreement or negotiation if you quickly need one core more, or if you want to configure it in a different way. So the source code of the RTL is fully open. You can verify it, like Bosch, who is working on functional safety to make the course ready. That is just one of the varieties you can do. And I think as a community, what we are also seeing in the software, if we are working together, if we are leveraging each other, and then everyone build on top of this, we are having a faster time to market. And also with Open Hardware now headquartered in Brussels, I think it's also an European initiative, helps us to get more of the sovereignty, which maybe we will need going forward. That brings me to almost the last slide. So call for action, visit the OpenHW Foundation. You have a great YouTube channel with a lot of teaching material, how to do verification, how to do software porting. There are a lot of things on it. The code is on GitHub. And yeah, that brings me back to the last picture, the open hardware. So you can see we are making the core, the tool chains, a little bit in the real-time operating systems. And now I would like to hand over to the next speaker, who is going a level up more in the software side. Before I hand over, are there any questions? Yes, sir.
Pardon my ignorance, but you said that RISC-V is already everywhere in AI and it will come to the automotive sector. Why is that? Can you explain to me? Because I'm not a hardware guy. So is it so attractive to OEMs because they do not have to license anything, or what's the point here?
Excellent question. Sorry, I skipped this part because that's a very important question. In the past, you had a variety of different architectures, especially one very dominant architecture, the ARM architecture. And don't get me wrong, ARM is a good architecture. They have a good code base, but it's one code base and every customer get the same code base. You're normally not allowed to modify it, so you need to use what everyone else is using, and you need to try to innovate with software or work around this. Also, when you're putting it into a chip, you're kind of limited. So if in the middle of the project you get a new AI algorithm and you want to change, or if you want to add more cores, you will need to go back and explain again. With RISC-V, there are a lot of things why I personally feel it's better. So RISC-V first is a modular architecture. That means it's a little bit like playing Lego. You have a base building block, and then you're adding features like an multiplier is an extension for RISC-V. So you can say I do the multiplication in software and I have a small code. I save cost when I make tens of millions of devices, or you say, I need to be more time critical. I put a hardware multiplier inside and I'm being more fast with this. So this modularity is a big thing. And also RISC-V brings something which is called domain-specific architecture, which allows people to add custom instruction. Now, for a lot of software guys, that sounds sometimes horrible, but it really depends how you're looking onto it. If you're making, for example, a closed system. Let's say you're making a Wi-Fi controller. I don't want to take an automotive example. You're more expert than me. You would kill me. But let's say you're making a Wi-Fi controller. You need to have this core to control it. You choose a RISC-V core. And then you say, I need to send the sequence to the modem, or I need to fine-tune the analog digital for the Wi-Fi signal strength and everything. And normally the core would have a few sequences, like 20, 30 sequences to run through to do all this tuning. You could make a custom instruction to say, I have this custom instruction, and if I'm writing 1, it sets the analog digital to the lowest. If I write 256 to the highest. So with this one instruction, you can really adjust it. If you have a closed system like this Wi-Fi controller where you're normally writing the firmware, and no one else, your end customer only has an API to connect to it, I think that's a great use case because it can save space, it can enhance or bring a faster computing capability to your chip. So domain-specific architecture is really a big thing. I believe that is also something which could make sense and will make sense, I believe, in automotive, because in automotive we have the problem we need to be always real-time, always very fast. So with this domain-specific architecture in a kind of closed system, we could be more faster, we could save more time, and RISC-V allows you to first customize the chip, take the building models you want, so you can put the chip and make it very performant or very small area for having it more cheaper to produce. And then plus adding custom instruction, you also can speed up times. You have a lot of things you can benefit from. Now, there are proprietary RISC-V architectures. You can license them. That's still okay. But with an open source, then you don't need to license it. You just take it like Bosch, make a proof of concept, see if it's working. You can take 1 core, you can take 5 cores. You are more flexible. Plus, with an open source solution, you also can inspect the code. And the thing is, every chip you're doing, you need to have this kind of core inside this brain to control your chip, to write a software that can be very simple, very complex, but you always need to have it. And then you're innovating around this. You're adding your know-how for a brake controller or for an ADAS system, how you do it on top, or for the infotainment system. That's your know-how. That's not what you're sharing, but the core itself, you always need to have the same. So if you are sharing this with other people, if you are having an code which can be inspected, you're reaching also higher safety standards, because maybe company A looked and found something and company B looked different and said, yeah, but we still need to adjust it one more time because there could still be. So that's why I think RISC-V will come in the automotive. This possibility to inspect the code, to adjust it for the specific needs, and also to have a much more faster time to market. I think that is a driving force.
Every time somebody does these customizations, they will need to find somebody to actually produce the chip according to these new specs then, right?
That is correct, yes. So what?
That is not an issue.
That is normally not an issue, yes. So the question is, if someone is changing something in the chip, you need to reproduce it, yes. So if you're having an adaptation or something, you need to make a new chip. If you already have the version A, it's normally not a problem to produce a version B, which is slightly changed. That's then normally a business case. Because producing a chip, you need to find a foundry like TSMC in Taiwan, Global Foundry is in Dresden, or maybe Bosch in Reutlingen, which then can adjust the chips to your needs and produce them. And that's a business decision, how much the chip production costs.
Yeah, so guys, please use the microphone, otherwise online we can hear you.
Okay, thanks for the good presentation. In this case, open hardware platforms, like how the security certification, who is responsible for that? So when it comes to the security certification, like common criteria certification.
That is a very good question. So we are not doing the certification right now. This one chip I mentioned, which is used in a root of trust, that was actually driven by Silicon Labs. So they have helped to drive it. There are things like having for each command the same time before returning an answer, hardening it against side channel attacks and so on, but we are not doing a certification for it on top, because you will still need the algorithms for encryptions and so on. So that's what the people who are using the chips are then doing themselves. What we are now considering is for automotive functional safety, so ISO 26262. Here we are working on a concept with some of our members, how we can bring this to the open source. And the problem is really the certification. You can make the core, you can have all the things inside, like Bosch contributed an awful lot of cool things for this functional safety readiness, I would say. But to do the certification, it's again a pure business decision. You need to put money on the table to get all the tables ready. And here we are working on possibilities how to do this. Maybe something like for members only. We're honestly not fully sure about it. So if you have a good idea, more than welcome to share with us. But the core itself, so the idea is right now, the core itself, functional safety, we keep it fully open source. Everyone can take it. Everyone can certify by themselves. But if people want to save this, like creating the certification, they could then join the open hardware and only members will get this. That's an idea, not decided yet.
One quick last question.
Yeah,
I'm not good with quick answers, sorry.
I'm also not a hardware guy, so this might be a completely stupid way to ask this question. But between, let's say, the scopes that you've got on the slide there, maybe the working groups, task forces that you've shown earlier, where does the microcode happen? Like, is that a thing? Is there a repo? Like, how does that? Where does that fit?
You're defining microcode like we have in x86,
For example,
okay.
do you have nothing there? Or is
So-
there nothing in ARM architectures? I just don't know.
The microcode is especially, so x86 is very strong for microcode. It is defining how this the problem is with x86 is it's a CISC architecture, and the microcode is basically helping to break it down in RISC instructions. We are already a RISC instruction, so we are reduced instruction set. We don't have the need to break it down. That's why we don't need a microcode currently. I can imagine once we're going to more high performance CPUs, something like the main processor of your mobile phone, where you have complex cache systems, where you have complex pipelines and so on, then it might be possible that we are introducing a microcode at that stage. But currently, the simplicity is still at a level where we don't need to manage this. If you would bring something like this, it would be here between real-time operating and tool chains.
Thank you.